Good afternoon, everyone. Today we'll see more in detail of what does the RF pulse do and how do we hope to get the signal out of the magnetization. So let's start with any doubts that may be present. So if I can request Deeptanu to unmute and ask the question, that'll be more helpful.
Yes, sir. The question was regarding once we remove the perturbation,
Yeah.
so there's only the magnetic field which is static about
Correct.
z-axis. So
Correct.
as the torque decreases,
Yes.
the the frequency of spinning will also decrease. So
That is correct.
so
Huh.
we fixed our rotating frames frequency which is omega. So how will it be affected? Like
We will see that in a simulation, hopefully, which I can get to in today's class. I understand your problem. The problem is we have multiple magnetic fields. You're asking, this is time dependent during which a torque will exist, but after this is gone, there'll be no torque. What happens to the magnetization in the lab frame after the pulse or in the rotating frame after the pulse, correct?
yes, sir.
Yeah. So I'll try to answer that as we go. The short answer to it is that the magnetization after the perturbation in the rotating frame will remain static. On the other hand, the magnetization that you have tilted to the transverse plane in the lab frame will precess about B naught. Okay?
So, but after some time, it will again go back to its.
It will go back. Okay. This statement I made, assuming there's no relaxation, be it transverse or longitudinal. Okay. But in reality, you'll have both the relaxation happening. We will see a simulation. You'll be able to understand. Or should we do the simulation and then go to the theory? Let's do at least a little bit of theory because otherwise I'll fall behind. Okay. All right. Any other questions from others from Tirunelveli or Pune? Please speak up, unmute and speak up.
No, sir.
Thanks, Puneet. Anybody else from Tirunelveli? Gauri, Onkar, Priyadarshini?
No, sir.
All right. Anybody else? Okay. Any questions from Bhopal? Please raise your hand. Yes. Good. How can tau C be defined for a non-spherical molecule? That's a very good question. To make our life easy, we'll only talk about molecules that can be assumed as spherical. Proteins are generally spherical. But if you end up taking something like nucleic acids, they are non-spherical in nature. Let's say you take duplex DNA, it's going to be like cylindrical rod. And even proteins are asymmetric. Not all proteins are spherical, right? So at that moment, the tumbling will be defined across two axes. This one, tau C, is defined only along the principal axis of symmetry, meaning that you would have defined a Cn for it. Along the Cn, you would get the tau Z measurement. But the moment, let's take an asymmetric molecule, like a cylinder. At that point, you have two axes of rotation, one along the axis of the cylinder, one perpendicular to it, right? So then a tau parallel and a tau perpendicular gets defined. Because you would realize that rotating about its cylindrical axis, if the cylinder is long in height, would be much easier than rotating about its perpendicular axis, right? So you can still define multiple such time correlation functions. So this is basically a correlation function between two molecules and how long does the memory of the relative orientation between two molecules exist. At tau C, they forget, right? And then two other molecules may have some information between them, but after a period of tau C, they forget. Yeah. So there you would have two such taus. And especially the tau that is shorter dictates your overall this thing, right? If you end up forgetting that information, that decides your overall this thing. So the whole point that I wanted to drive from here, irrespective of that, would you be ready to accept that the tau, even for the asymmetric one, will scale with the size? Isn't it? As the molecular size becomes bigger and bigger, tumbling becomes smaller and smaller. This overall direct proportionality of rotational tumbling time and the size remains. If at all gets worse for asymmetric molecules in comparison to spherically symmetric molecules. Makes sense? Yeah? I hope I answered your question. Any other questions? Please feel free to ask. Okay. Yes.
You mentioned in the last class that Tausi, in some NMR experiments, we keep the temperature low.
We may want to keep the temperature low. And in cases where, let's say you have an exchangeable proton, which is, say, weakly hydrogen bonded or even hydrogen bonded. Remember, this is still acidic in nature, meaning that if you have a solvent which it could engage with, after some point of time, you could have a scenario where you would have had something like this. You would have had a scenario where chemical exchange has taken place due to exchangeable proton. And let's say this process, we have to put a two-way arrow here. There's an equilibrium, right? What could go forward could go backward as well. This process, if the rate kinetics of this process is much faster, then you will get an average of chemical shift of what it experiences here versus here. On the other hand, if the process is very slow, what do I mean by very slow? You have a certain acquisition time and the exchange happens slower than the acquisition time, then you would get two NMR resonances, one for each, with their population being the integrals. Okay. On the other hand, if the exchange rate kind of matches with the acquisition time, you will not see anything. Okay. So in these kind of cases where the exchangeable proton information may get lost, in order to reduce the rate kinetics, because the rate constant is generally proportional to e power minus Ea by kT, and therefore if you reduce the temperature, the rate kinetics reduces. The rate kinetics reduces, you jump out of the regime where in NMR you don't see a signal, and therefore you may get a resonance. So if you do not see a resonance that you anticipate to see, it could be that its exchange broadened, meaning that the resonance should be there, it's not there due to other reasons. For instance, let's say we take ethanol NMR spectrum in D2O. What's going to happen? The OH will become OD because you are DOD, which is heavy water, and you'll get exchange. So you'll never see the OH in a 100% D2O sample. On the other hand, let's say you do this experiment, ethanol in 90% water, 10% D2O, you would still see the hydroxyl proton of ethanol. But you would see that it's much broader than any of the other resonances of methyl or methylene, although the molecular size remains same. This happens because of the interaction of the hydroxyl with the solvent molecule to form hydrogen bond, break hydrogen bond. So it's going to happen as a function of time. It's also an equilibrium. There'll be some state that's not hydrogen bonded. There'll be some state that's hydrogen bonded, right? Some that's hydrogen bonded, two water molecules, or one water molecule hydrogen bonded, two ethanol molecules. There's a population of states that exists which defines the chemical shift of the hydroxyl. And as the rate kinetics also defines it, the relaxation rate increases, so you'll get a broad singlet equivalent. Otherwise, you should have gotten a triplet for the hydroxyl proton. So now if you end up taking the ethanol and CdCl3, where the exchange will not happen, there is no way the solvent will change the OH to anything. And there is no way the solvent will also engage in a hydrogen bond. At that point, for the ethanol hydroxyl, you'll see a triplet. Very small triplet. To resolve it is tough, but you can see it. So what I'm trying to say, it's the same ethanol molecule. Depending upon the condition that you put it in, the interactions are different. When the interactions are different, the chemical environment changes. Chemical environment changes, it affects the chemical shift. So in such a scenario, if you want to define a structure of a biomolecule where these kind of interactions is what drives the secondary structure, tertiary structure in terms of alpha helices, beta sheet and whatnot, maybe you want to reduce the temperature to trap them in the hydrogen bonded state to get it. Okay. At that point, you should keep in mind two things. As you reduce temperature, of course, if you're running it in water, you should not try going less than 0 degrees Celsius, in which case water may freeze. Why am I saying water may freeze? Because you still have salt in it. Salt results in depression of freezing point, right? Reduction in freezing point, colligative properties. But even then, you shouldn't go very low in temperature where water freezes. If water freezes, it becomes not solution, it's a solid. That's not the only problem. You should have this in mind because what happens when water freezes? What happens when water freezes? One of the important physical properties. Water expands upon freezing. Okay, and due to which the NMR tube might shatter inside what you're doing. So you should be very careful playing with the temperature. On the other hand, higher temperatures, of course, water may be okay at 45, 50 degrees. But remember, if you're working with organic solvents, the solvent might evaporate. Something like CdCl3, you should not go higher in temperature. On the other hand, something like DMSO is very interesting. It actually freezes at 18 degrees or something, maybe 15 degrees. Okay. So in a very cold winter in some parts of the world where it's 10 degrees or even 5 degrees, you'll actually find, although it's a DMSO sample, it'll be like solid. It will not move at all. Right? So you should not run, you should be very aware of what are the effects of temperature on your sample and NMR characteristics. So when you're choosing a temperature, you should have an appropriate choice of why you're choosing the temperature. Let me give another example of why you want to run it at high temperatures. There are some molecules called membrane proteins. What are membrane proteins? Membrane proteins are proteins that are involved in the plasma membrane and are very important for biological function. These many times pave the way of signaling across cells, and therefore these are proteins that are embedded in lipid bilayers. And if you want to mimic similar situation in a test tube to study them, then you have to put lipids in them like bicelles, micelles. There are many such model systems to put them in. Now what happens, the protein is of a certain size and you enclose it into a micelle environment or a bilayer environment where it gets incorporated to mimic the real life scenario. The molecular size increases much more than actually the size of the protein. At that point, the size will be much, much more than what you anticipate because you're not looking at the tumbling of the protein, you're looking at the tumbling of the entire bilipid layer along with the protein so that you can study the protein in a relevant context. Then you might always ask, why do you put the bilayer to make your life difficult? If you put it in water, maybe it will not be happy, it will unfold. But you want to study them in a biological. So at that point, you would want to increase the temperature to 45 to 47 degrees still to measure them, because then you'll increase the tumbling of the lipid bicelles or whatever. But of course, you should also have in mind the system that you're using should not have a phase transition. There are many times where such lipids also undergo different phase transitions. So what I'm trying to drive overall, when you're trying to do an experimental setup, you have to have an overall idea of what kind of buffers you're going to use, what is the pH that you're going to use, what are the salts that are going to be there, what is the temperature you're going to put it in. This should come as an informed decision. It's not a random thing that, okay, set it at 25. If you can set it at 25, you would probably set it at 25. But there are many times where going away from 25 matters. And when you're going away from 25, you should have valid reasons why, or rather, going away from the temperature, room temperature, you should have valid reasons to go away from it. When that is happening, please be aware of the sample that you're using because the sample characteristics change. Be aware of the NMR characteristics, that will also change. And many times you'll see a outcome based on it. The same ethanol in CdCl3 versus DMSO-D6 versus D2O versus H2O-D2O will slightly have different spectra based on the interaction of ethanol with itself and ethanol with the solvent. Okay, but it will not change the methylene chemical shifts as much, but it has a larger effect on the hydroxyl chemical shift. Although I didn't answer you directly, I hope I made it clear to you that please be aware of the fact that temperature is an important phenomenon that you could exploit to make your spectrum look better and therefore still derive the information. Any other doubts, questions? Okay, let me continue now. Let's quickly recap what we did in the past several classes. We said nuclear spin not being zero allows us to study them when suspended in a magnetic field, and we are focusing more on a spin half system, which will have two degenerate states, allowed states, alpha and beta. When suspended in a B naught, results in quantum magnets that align themselves at an angle with the main magnetic field and breaking the degeneracy of these two states. Since the two states are not degenerate, they will have a population difference. The population difference results in a bulk magnetization for the sample, which is all the information. We were also able to understand from last class that this bulk magnetization cannot be measured that easily when it's along z-axis. Therefore, you want to disturb it. When you disturb it, it comes to the transverse plane. Here, I'd like to point out, I may have made a mistake in the last class saying that if you apply an X phase pulse, you'll get the magnetization along Y. You'll actually get it along minus Y. It was a small mistake I did, but we'll correct it as we go today. Okay. So once you get the magnetization, the RF pulse that you apply that disturbs the bulk magnetization gets it to the transverse. Then you turn off the RF. Then yet again, you have the M cross B, which will take into effect where the magnetization starts to process about B naught. And when that happens, it cuts the coil that's present, and that induces a current, which we measure, the signal what we call as a free induction decay, which when we Fourier transform, we do a complex Fourier transform, where we get the cos part and the sine part, and do a complex Fourier transform to get a NMR spectrum in the frequency domain. This is where we were. And then slowly we started to look at what is the rotating frame. And here is where we also defined a state where, let's say, instead of visualizing it in the lab frame, we will go to a frame of reference, which helps us kind of negate visually the effect of B naught on the magnetization. This is a mere change of coordinate system if you want to understand. For instance, when you would have seen many of these examples when you did quantum or other courses, you would have changed the Cartesian frame of reference to something like spherical polar coordinates. That will not change the features of hydrogen atom. That just changes the way we want to extract the answer out of the system, just to make your math easy. Similarly, we are also doing kind of a coordinate transformation. The major change here is that the coordinate z-axis for the lab frame and the rotating frame, the z-axis is collinear with respect to each other, while the x and y axis for the lab frame is static, while for the rotating frame, it rotates at a precession frequency of omega, which is how we defined what is omega naught, where we said when omega naught matches the precession frequency, that's defined as a Lama precession frequency, which is where the minus gamma B naught comes. I just put the k part of it saying that the rotation is about the z-axis. Why do we want to rotate about the z-axis? The precession is also about the z-axis, and therefore you want to match the motion of the spins with your rotating frame so as to negate the effect of B naught. And then we looked at what happens when you put it in the, what happens when you apply an RF pulse. We said that the RF pulse has an amplitude followed by a sinusoidal part. This is where we said this is a linearly polarized light that can be decomposed into right circular and left circularly polarized light. And how did we do it? Just a simple math representation of 2A being A plus B plus A minus B, where the minus B part gets cancelled with each other, and the 2A part is what you started off with. The reason why we did this is that let's assume this is one type of rotation, while this is the other type of rotation, meaning precession. Only one of these components would end up interacting with your spins based on the gamma. And the other component more or less has no effect. Even the effect it has is termed as the Bloch-Siegert shift, which is proportional to B1 over 2 B naught the whole square. What do I mean by this? Is that it's not like the other component will not interact at all. Let's assume that this component interacts and this component is in the opposite direction of rotation. It doesn't mean this doesn't interact at all. It interacts, but to a very, very small extent. As we go forward, you will realize that the B1 is generally applied for in kilohertz, this thing, and the B naught is in megahertz. Since it's a ratio of kilohertz to megahertz power 2, you realize that the effect that the counter-rotating light will not have much of an influence. This does come for something called soft pulses, while hard pulses will not see it, but we are going to keep that away for the discussion for most part of the course. So remember, if you're going to a little more advanced part of NMR, where you're using something called shaped pulses or soft pulses, which we'll probably invoke after the midsem, this may be important to look at. But for most of our conversation right now, you can assume that this goes to 0. So only one of the parts interacts with your spins, the other doesn't. We don't have to worry about which one does and which one doesn't. Okay. For this discussion, we'll say that this part ends up interacting. And the important aspect that I said is that the omega RF is what should be very close to omega naught that is being set up. Now, what's going to happen? Yet again, let's go to the analogy that we were trying to think, where a mom is trying to feed a baby in the merry-go-round. So the mom's frequency of running is omega RF. And the merry-go-round that's running itself has its own omega, which is omega naught based on its chemical shift and whatnot. Here, I'm obligated to explain a little bit more about the features of NMR spectrum before going forward. Since I've mentioned the ppm scale, so I'm going to plot chemical shift. Let's say 0 ppm is set somewhere. Let's think of an easy case scenario where your methyl peaks come at 1 ppm and methylene at 3 ppm and hydroxyl at 5 ppm. The case of ethanol, just for the sake of example. You realize that each of their precession frequency is based on their shielding parameter, right? And if you want to measure the spectrum where only these three lines are being present, I would keep the carrier. What do I mean by the carrier? The omega RF. I can either keep it on this resonance, or this resonance. You can never be on resonance to all three of them simultaneously because their precession frequency is different. Okay? Just to highlight even further, let's say we are working out in 500 megahertz instrument. You would realize that at that one point, 1 ppm will be equal to 500 hertz. Therefore, if you keep your carrier on 3 ppm, then this is going to be something like the carrier minus 1000 hertz, while this is the carrier plus 1000 hertz. Why is it always a good idea to keep the carrier in the middle? Because you would soon realize the pulse that you're applying also has a profile called bandwidth of excitation. Meaning that if you want to treat all spins equally, the disturbance should also treat them equally. Okay, and therefore keeping it in the middle would evenly more or less distribute on either side of it. We'll see more of such characteristics as we go forward. So what do we mean by omega RF? Omega RF is where you keep the carrier position, and of course on either side it will have a excitation profile which is more or less flat, and therefore you'll be able to study what's going on. Okay, so the omega RF that we are trying to look at will be kept on one of the spins, the others will be off resonance. Yet again, for block simulations, or rather block equations, let's keep our life a little simple and only talk about the water molecule because it has only one resonance, and you can keep the carrier on that resonance. There is no offset, right? Okay, so let's understand for that scenario, and then we'll extend it for ethanol while hopefully when we finish the class today. Okay, so once that is done, let's say we are going to the rotating frame. What is going to happen? You realize that when you have a camera that looks at the mom running at the speed of the merry-go-round, at the angular frequency of the merry-go-round, the mom and the baby and the merry-go-round are static. So what is going to happen when you are able to precess at the frequency of the Lama precession frequency? This component goes out. Okay, and what is going to happen is that any contribution or mismatch with this component will come as residual B naught field. Why are you doing this? Largely because you want to negate the effect of B naught. Think about it. You have an elephant in terms of B naught, which is in megahertz, and you want to defeat the elephant with an ant, which is your B1 in terms of kilohertz. How can an ant kill an elephant? That's the question you're trying to ask. How does the ant kill an elephant? It goes onto its ear and irritates the elephant and kills it. Similarly, you have a precession frequency that's matched on resonance, meaning that the few kilohertz are on top of the megahertz, and you go to the megahertz, and therefore the entire B naught field kind of gets lost. But of course, as I just explained to you, there will be situations where you can only keep one resonance online, the others will be off resonance. This off resonance is denoted as capital omega, which will go as omega naught minus omega RF. What do I mean by this? Even for the water molecule, which has only one resonance, when you're starting the experiment, maybe you do not know where the resonance falls and you might have kept the carrier elsewhere. Let's say the resonance falls at 5 ppm, but you started the experiment by putting the carrier on 4 ppm. It's still the off resonance will exist, right? And then after that experiment, you can, okay, I have to move 1 ppm, you can move it and keep it on resonance. But it's not a hard and fast rule to worry about keeping at least one spin on resonance. All you want to make sure is that the window within which your peaks fall are definitely measured, are definitely disturbed. We'll worry once again about this when you go to the acquisition parameters on what decides the spectral width. Okay, spectral width is the window that you want to see your resonances in. Let's say 0 to 10 ppm is your spins. That will be your spectral width you want to measure. You would rather keep the carrier at 5 ppm and have a spectral width of 10 ppm. Okay, 5 ppm plus minus 5 ppm. If you want to have 0 to 15 ppm, there are multiple ways of doing it. You can keep the carrier at 7.5 and have plus minus 7.5. But many times you will realize that you cannot keep carrier wherever you wanted. You generally want to keep the carrier on the solvent. And if water is your solvent, you cannot move it away from 4.77 ppm or 4.8 ppm. And therefore, if you want to, let's say water is generally coming at, just for the sake of discussion, I'll put it at 5 ppm. It comes at 4.7 ppm and it's also dependent on temperature. So one has to remember that. But let's say water comes at 5 ppm and you want to measure 0 to 15 ppm. Then, although you just want 15 ppm spectral width, since you're not keeping it in the middle, you want to make sure 5 ppm plus minus 10 ppm is the spectral width, which is 20 ppm must be the spectral width. Makes sense? So you will unfortunately also measure 0 to minus 5, which you don't care about because maybe resonances don't come. But the mere fact that you're compelled to keep the carrier on water for some reason, and you want to make sure 15 ppm is measured, so 5 to 15 is 10 ppm. Whether you like it or not, you keep 10 ppm on both sides. Okay, and the position where you keep the on resonance pulse is called the carrier frequency. And the entire width that you want to measure your spectrum is generally referred to as spectral width. And when I was discussing all this, I also slipped another word called bandwidth. The bandwidth is dependent on the disturbance that you're applying. The bandwidth takes care of whether the disturbance that you're applying is treating within the spectral width all the spins, how equally or how far from equal. Just to give an idea, I'm teaching about 12 students right now. Pretty sure the lecture I'm giving is constant for all of you, but not for everyone. The concept I'm trying to teach reaches equally. Okay, you can think of that as the bandwidth. As long as I'm able to make the concept understandable for all the 12 people, I think my bandwidth of excitation has been uniform. But I'm sure you guys are able to appreciate the fact that some of them will not understand, some will understand more because their background is more in the field, right? Anyway, so the important part is to remember the carrier frequency is omega RF, and any deviations of omega RF from omega naught for that given spin results in offset. Offset from the carrier, which is defined as omega naught minus omega RF. This offset allows for the B naught to be not completely erased out. Right? Because once again, now think of an example. Now think of an example where the mom runs slower than the merry-go-round. Right? What's going to happen? She's still going to see the merry-go-round move faster than her. What did we want to do? We did not want to have the motion of the merry-go-round, but now that's going to still exist. So that residual part, you can imagine, since you are applying the B naught along z-axis, is the delta B naught. So now I'm going to draw the magnetic fields that we are applying. In the rotating frame. So therefore, what I'm going to write, x rotate, y rotate. Z can be rot or non-rot because you're rotating about that axis. But let's, for the sake of consistency, let's do it this way. So you're going to have delta B naught. Remember, delta B naught could be negative as well. For instance, the example that we just took a moment earlier, when your carrier is kept on this, one is going to be negative offset, the other is going to be positive offset. You could always imagine a scenario where you keep the carrier on the methyl group, in which case both are positive offsets. You can yet again imagine a scenario where you keep on this and these are negative offsets. The reason why we don't worry about where we keep it, what's positive, what's negative, is largely because if you're trying to probe a molecule that you have not seen the NMR spectrum of before, you do not know where the resonance has come. Your only target will be to keep a broad enough window to make sure all resonances come within it and excite it to see where it comes. And then maybe move the carrier to minimize spectral width. There are reasons why you should minimize the spectral width, but let's not go to it right now. Make sense? Okay, with that being the case, so delta B naught could be pointing along z-axis or minus z-axis. Please remember that. Currently, I'm drawing where the offsets are positive. Okay. Then what did we say? We applied a magnetic field B1 at a phase angle phi. And therefore, what is going to happen? The projection of this is going to be B1 cos phi projection along y is going to be b1 sine phi, and then this is going to be given as delta b naught. So right now you have two magnetic fields, and therefore what is going to happen? You're going to have a resultant magnetic field. This is based on the parallelogram law. I'm sure you guys may remember this. We make a parallelogram, the resultant is going to be somewhere here. Okay, which we are going to call as B effective in the rotating frame. The textbook just calls it the BR, but so that you remember that it's a rotating frame and there's the effective magnetic field. Okay. Why are we worrying so much about where is the effective magnetic field? Please recollect the expression dm over dt in the rotating frame comes up to be something like m cross b, the gamma somewhere. Gamma is here, right? Right. So we have to always have a mind on where is b. You need to know where is m, and therefore you understand precision of m about b. Yeah. So now that being the case, therefore what is going to happen? B effective, the vector is going to be b1 cos phi I cap rod plus b1 sin phi j cap rotating frame plus delta b naught k cap, where this delta b naught is dependent on offset. I hope I wrote it right, where the delta b naught is dependent on offset. Okay. Once again, this comes up because you cannot be on resonance all the time. In the case that offset is 0, this part vanishes. Okay. And these parts are confusing you too much. You can always imagine an X phase pulse that you applied, in which case phi goes to 0 and therefore this part goes to 1, phi goes to 0 and this part goes to 0, and none of these exist, only B1 exists along the X phase. This was the experiment that we were trying to understand. So far so good. Any questions? Please raise your hand or unmute and ask. This matters because if you do set phi to 0, let's put phi to pi by 2, in which case the pulse goes here. I mean, the blue vector would be along the x-axis, and then you can allow the magnetization to move. This was a mistake that I did last class, where if you're having B1 along x, the flip will be along minus y, not plus y. I was trying to draw everything along plus y. It's always a counterclockwise rotation in a right-handed coordinate system. Okay. And why is it always like that? Let's take an example and take a look. If visualization is a problem, let's say we are starting from thermal equilibrium. So thermal equilibrium, the m vector is going to be m naught times k cap. Okay. And let's say you're applying a pulse along x-axis, that's going to be b1 I cap. If you're talking about m cross b, you're going to have k cross I, which should be j cap. But remember, there is a minus gamma that comes for omega, and therefore it will be along minus y axis. Okay, so here we are only talking about m cross b, but there's a minus gamma component, which is what defines the omega. This is very important because if you understand precession, you understood a lot of things in NMR. Because it's a repeated application of precession, be it spins, which we will see in the quantum part of it within maybe 2 weeks from now, or for the classical part. If you understand precession, you understood NMR. I hope you have understood how the bulk magnetization comes, and hopefully this BRF pulse is able to understand, okay, you're going to play with the B effective to make M naught dance to your tunes. The moment you have the power to make it dance to your tunes, you apply the pulse based on wherever you want to get it, and you'd be able to achieve whatever you want. Make sense? Okay. With that being the case, what are the other few parameters that we have to define? So let's define an angle theta of the effective magnetic field with respect to the B naught. This is important to understand because, let me write the expressions and then it'll make more sense. If you see tan theta, what is going to be tan theta? Tan theta is going to be adjacent by opposite. right? So that is going to become delta B naught divided by B1. And then let's say we multiply by minus gamma B naught, sorry, minus gamma. Let's say we multiply by minus gamma. I think I'm making a mistake here. No, it's going to be, you guys accepted to my wrong definition. Tan theta is opposite by adjacent. So it's going to be B1 by delta B naught, isn't it? Yeah, nobody raised it. I'm blatantly making a mistake. Huh? Be awake. I know after lunch it's tough to be, but which will become omega 1 divided by capital omega. Okay, this is a very important expression where theta. Why does theta matter? Why am I spending time on this? Is because if you guys are able to understand how far the effective field is from Z, then you'll be able to make your rotations easier. So that's the whole purpose that this expression solves. So tan theta is going to be B1 divided by B naught. I hope I wrote it correctly. Right? Yeah. So therefore, what's going to happen here is that if the field that you're applying is strong, let's start with something easy. When your offset is 0, you realize that theta is 90 degrees. Because something by 0 is not determined, and tan inverse of its infinity will be 90. So that means if you are applying an on-resonance pulse along the x-axis, the B effective is along the BRF itself. Alternatively, if it is off resonance and it has a positive off resonance, it's going to be a net vector that's going to be contained in the ZX plane. Right? On the other hand, let's say the spins have a negative offset, then the delta B naught will be inverted. You're going to have something like this. Effective of this and this is going to have B effective in the minus Z plus X plane. This is important because as long as you have the RF along x-axis, the precession means the magnetization inscribes a circular motion about in the ZY plane. Correct? Let me repeat again. When the RF pulse is on resonance along the x-axis, the M naught makes a circular motion about the ZY plane, Z minus Y minus Z plus Y, Z, and it keeps on going. How long it keeps on going? Until you keep the RF pulse on. The moment you turn off the RF pulse, wherever the magnetization was, it remains and will then get into the influence of B naught because the RF pulse is turned off. Deeptana, I hope that explained a bit of the question you had, but we will see the simulation and that may help. Or maybe I'll give the simulation for you guys to play around with. Okay? And therefore, this is an important thing to understand where is the effective vector with respect to the pulse that you're applying. And you're able to realize on resonance, this is more or less, on resonance is 90 degree, but as you start to go away from on resonance, you realize that the theta is going to be on the ZX plane. And therefore, at that point, once again, the cone starts to come, although it's a very big cone that comes, it's not circular anymore, right? This visualization matters. Now, to something called the flip angle. Alpha is defined as a flip angle, which defines the angle from where you started in the magnetization, where do you end up, okay? And it's generally given by the omega r times tau p. What is omega r? Everywhere omega that you have, it's going to be given by gamma minus gamma times b. Since we are talking about effective angular frequency, you're talking about effective magnetic field in the rotating frame. Of course, all are ROT. I'm going to stop writing ROT from here on. Okay? And what is BR? Let's take a look at BR, which is B effective. This is going to be nothing but B1 divided by sine theta. So BR is going to be B1 divided by sine theta. Largely because sine theta is B1 by BR and therefore BR is B1 by sine theta. So therefore, what happens here is that if you're going to have something like this, minus gamma BR tau p, is going to be minus gamma B1 tau p by sine theta. which makes it omega 1 tau p by sine theta. This is why theta matters, for you to understand that flip angles will not be the same for all the spins because you can only be on resonance with one spin. So although you want to execute a 90-degree pulse for all of them, for on resonance it will be 90 degrees. As you start to go off resonance, it will be slightly more than 90 or less than 90. Remember, sine theta, maximum value is 1. And theta is 90, you're going to have the flip angle that you wanted. So you may always set up omega 1 tau p to pi by 2 and pi by 2 divided by sine theta, where theta goes away from 90 degrees, you realize that it's going to be greater than 90 degrees. So does that mean the spin goes away from y? No, not really. Remember, the motion for anything off resonance is not circular, but it also inscribes a cone. So it's going to be slightly curved with respect to whatever you had on resonance. So it may not end up along minus y for this pulse. Okay, it'll be slightly, it'll also have a slight z component because the precession is not nicely circular, but it's more conical. Okay, this is what will result in something called a phase error, first order phase error, but we will keep that out for the time being. Okay, now slightly I introduced a parameter tau p. This is called the pulse width. This is the duration of the pulse that you're applying. As I said, until you apply the RF pulse, the magnetization will dance to your tunes. So therefore, you can choose when to turn off the RF pulse to get the orientation of magnetization wherever you wanted it. So if you want a pi by 2 pulse, you would have kept the pulse on until it reached the minus y axis. So it's within your power. You would say, okay, it's 10 microseconds, 5 microseconds, depending upon the sample, depending on the spectrometer. So you get to calibrate the 90-degree pulse for a given spectrometer and a sample after setting up the experiment in a proper way. Make sense? So therefore, what's happening here, I've defined quite a number of things. These are called block equations, where you're trying to understand how does the magnetization change as a function of time. If you may remember, the first expression I wrote as dm of t by dt is given as m of t cross gamma b of t. I hope you're able to understand magnetization can change as a function of time. The fields can change as a function of time. You have the power to have both as a function of time or neither as a function of time and whatnot, but you'll be able to predict what is going to be the outcome. How does the magnetization change as a function of time? Everybody confident? If not, if there are any questions, please unmute and ask. Any questions here? None? Anybody from Thiruvananthapuram or Pune have questions? Okay, let me continue. What else did I want to say? Okay. So therefore, what matters at this point of time is for us to understand how does the magnetization change its function of time. Should I introduce relaxation now? Yeah, maybe I could. So there are multiple components to the m of t. What do I mean by this? You have an x component, you have y component, and you have the z component. You are able to see how the entire stuff plays out when you started off from equilibrium. Let's take water as an example because that's what I promised to start off with. Let's say we take water as the example where only one resonance exists and you kept the carrier on water. What is going to happen? Water's bulk magnetization will be tilted, and in the rotating frame, it's going to remain static. And as Deeptanu was trying to also make us understand, it's not going to remain forever. It's going to decay as a function of time because we know for a fact, after we turned off the RF pulse, the phase decoherence starts to kick in. So therefore, what Bloch said is that he said it's proportional to the amount of magnetization that's present along the x-axis. I mean, transverse plane. It's not exactly this, but let's write it this way. Meaning that the more you have as a function of time, that will decay as a function of time. This is literally first order rate kinetics. Minus dA by dt equal to k times A. Just that I took the minus sign there on the other side, and the rate is R, not K. Okay, these are first order rate kinetics. And on the other hand, for something like the Z, it's going to be recovery of how far is mz at t minus mz of 0. Meaning, however far the current state is from the thermal equilibrium, it's going to recover back to it. I hope I wrote the signs correctly, minus signs. Let me double check. Many times while I talk, I make a mistake. So don't want to propagate an error. Yeah, for a change, I wrote it correctly. Okay, the textbook says this is m naught, but not always you start with thermal equilibrium. There are cases where you see quickly we go away from thermal equilibrium. So therefore, this is a recovery of longitudinal magnetization, while this is loss of transverse magnetization. Okay, since I promised simulation, let's go to simulation and try to see what happens. I'll share this link. Okay, what you're able to see is a magnetization that's not in thermal equilibrium. Here you are not looking at spins, you're looking at magnetization. When the magnetization is not along z-axis, are you able to see there is precession going on for the magnetization about B naught? The B naught, what you see here is the gray line that you see along the z-axis. And the precession for the magnetization is about that axis. Are we able to see it? Okay. On the top right, what you're also able to see is the frequency, meaning that let's say you keep the detector along the transverse plane, let's say along y-axis, it's going to keep on cutting the current. Remember, the entire magnetization is not along the transverse plane. Maybe they applied a 30-degree pulse, not a 90-degree pulse. So it just came off Z. So there is still a transverse component, which is less than whatever maximum it can achieve. Nevertheless, it's a non-zero component, which will keep cutting the coil and therefore generate a current. And you are able to see the oscillation that's going on the top right, as shown by the red curve, right? Now, what we can try to do to the simulation is that let's put it back in equilibrium. I just click the button on the bottom left which said equilibrium. Now, what I'm going to do is to apply a 90-degree hard pulse. And what has happened? You moved the thermal equilibrium to the transverse plane. And what you're able to see is the precession of the bulk magnetization about the z-axis, about B naught. Which frame are we in? Lab frame, correct. We are in the stationary frame, if you realize. Let's say we go to the rotating frame. You see that the frame starts to rotate and your magnetization appears static. This is the M cross B part of it. So this is why we go to the rotating frame. Let's say we are in the lab frame. I want you to observe a few things on this. So let's go back to equilibrium. Are you guys able to see the shadow on the yellow plane that you see? Right now it's a dot, and after I apply the 90-degree pulse, it's a very long gray line that keeps moving. Basically, that's a projection of your magnetization along the transverse plane. And the length of it will determine how much amplitude comes on the top part. So let's go back to equilibrium. Now you will see when I say 30-degree hard pulse, you see that the length of the gray shadow is lesser than what you had for 90 degrees. Okay, so basically I hope you guys are able to understand. You start from equilibrium and you can apply any theta pulse along a given axis. Now let's see, just for the sake of looking at the effect of precession and the mean magnetic field, I'm going to apply a 90-degree soft pulse. Don't worry about what it means currently. Let's see what happens when you apply a 90-degree soft pulse. I'll explain what is the pink thing as well. You are able to see two things happen simultaneously. Precession is happening as the disturbance comes up. Okay, and this is important for you to understand that whenever you're applying a pulse, B naught precession and precession about B1 will happen along the effective field that we have come up with. By going to the rotating frame, let's do the same process again. Now I'm going to go to the rotating frame. I'm going to repeat the same pulse. You would see the motion of precession has been taken off. This is the main reason why we go to the rotating frame. We remove the effect of precession when you're looking at the pulse being implemented. Of course, this also happens in the hard pulse, but it's so fast that we cannot see it. And therefore, I applied a soft pulse, which takes a long duration to come up. Now, going back to the lab frame, look at the 90-degree hard pulse. What you're able to see as a pink vector that comes is actually the torque, which pulls the magnetization. Okay, that's majorly the difference between the hard pulse and the soft pulse. Soft pulse has a much smaller torque, while hard pulse has a much larger torque. It achieves the same thing in a much shorter time. The hard pulse achieves the same effect in a shorter time. Okay, so what I want you guys to do today as homework is to go play with this simulation. I'll share this and you can add relaxation to it. Currently, the T1 and T2 relaxation are infinity. Now you can always introduce T2 relaxation. See that the vector becomes smaller and smaller as a function of time. Take a look at the top right. You're able to see a free induction decay kind of this thing coming up. But the major problem with this experiment is that I've set R2 to be non-zero, but R1 to be 0. If T1 is infinity, 1 over T1 is 0. That means longitudinal recovery never happens. But that's not the real case scenario. So let's go back. And what I'm going to do is to also set T1 at a certain number. 9 seconds for T1, T2 is 4 seconds. Let's apply a 90-degree pulse. Multiple things are happening. The length of the shadow becomes reduced and the longitudinal recovery is also happening simultaneously. Are you guys able to see that? So the magnetization is an effective vector across mx, my, and mz that comes up. Okay, when you're looking at the mx, right now the mxy component has gone to 0. Okay, you can always also turn on whether you want to see the mz component as well. Yeah, view, you can turn on the mz component as well. Okay, let's repeat that experiment and stop today's class. If you hit it down, the mz component is coming up as the gray line on the top right graph where it slowly is recovering. Okay, so with that, since I'm already out of time, apologies for having come a little delayed. My request is that please read what has been done. I'll share the notes and also the video. I've not had the time, but I'll be able to share it. And tomorrow morning, we are having a class by 9. So please be here. So we'll make sure that we'll complete one more aspect. By that time, if you have done through the simulations and thought through about how relaxation works, we can go to the next series of steps. I hope to give you an assignment over this weekend. And the next series of classes, we'll try to catch up on how the NMR spectrum will work out for some of the systems. Okay. Thank you so much.